buttons and stuff. Okay, cool. Let's do it. Cool. The floor is yours.
Right. Okay. So I'm going to talk about shaders in Unity, both shader as we know them and compute shaders. Both the slides and the resources I'll be using will be accessible on the wiki page under shaders in Unity. So, yes, let's see. So, as I said, typical shaders, the ones we've been working with so far, kind of at least, and compute shaders will be after the break if I have the time. So, first part, we'll look into the sort of simplified rendering workflow in Unity and see that it's kind of comparable to the OpenGL pipeline, but I mean, the OpenGL pipeline isn't simplified in this case, so it's kind of hard to see, but you have sort of the core concepts with the 3D models, the vertices and stuff. You have the uniforms and the textures, and you have the shaders, of course, that is the pipeline. So in Unity, we have 3 different types of shaders. The first one is called unlit, which is kind of the most similar one to the ones we've been writing. It's called unlit because there's no inherent lighting applied, so you need to do the calculations yourself. So it's not really unlit unless like you don't apply the lighting, but in many cases you don't need any lighting as well, so it's a sensible name in that sense. The unlit shader type has all of the standard sort of shader stages, vertex fragment, geometry, and the tessellation shaders, not in that order. And then there's a Unity special shader called surface shader, which is kind of a more high-level shader than the other one, because you get a predefined lighting model you can just apply after, so you don't need to do all the fancy math around the lighting. You can use a predefined lighting model, or you can define your custom one, so it's kind of flexible in that way. And well, lastly, that means you don't really specify the color that is outputted onto your screen, but rather the surface properties, hence the name surface. The surface shader only has 2 stages, which is the vertex and the surface shader. We'll look at both of these later on. Then there's compute shaders, which I'll also be talking about later, if there's time. Compute is often used for rendering, or it's often used for rendering, but it doesn't need to be used for rendering at all. Can be used for all sorts of things. So, in Unity, there's this thing called Shader Lab, which is a language sort of wrapping around your shaders. The reason they have this is so that you can make more information and more control into your shaders. We started trying to do the same thing with our assignment 2 last year, where we sort of supplied the options to set culling mode and stuff. You can also do this through Shader Lab. The most important thing, I think, is the properties block, where you set up basically kind of uniform access points. I'll get back to that actually. Let's just point out a few things here. So you see all the keywords in the shader. You have actually quite a few of these. You have a shader, which is just a name declaration of the shader. So this is the thing you reference when you try to access the shader from code, and it's where you'll find your shader within Unity. You have the properties, as I mentioned, are sort of the uniform access points. You have subshaders, which are wrappers for a specific implementation of the shader. So if you write a really high-end shader, you might want to account for mobile devices as well. So you write another shader which is targeted at the mobile audience. But the shader itself is still called the same thing. And will automatically sort of compile to the target platform you want. And there's tags. Tags are sort of just, well, tags that is used by Unity to help try to order the passes, or the how or when the rendering happens for objects using this shader. Then there's a pass, which is basically when, which is basically the draw call, I guess. And then you have the possibility to have more than one pass. So in some cases where you have transparency, for example, we want to have first the front faces rendered. Then when you go through the cube, for example, you want to have the back faces rendered with this specific pass. So it's sort of just repeating the stack twice, both the vertex and the fragment shader. So you get sort of the first pass when you enter and the second pass when you go out.
So just for clarification, so tags would be used, so if you think about, abstractly thinking about the draw loop, right, if you like, right? So tags are for structuring the execution within that loop, right? And passes are managing the loop, right? How many passes you have, meaning how many iterations you have through the loop, right? For different things. Okay, cool.
And then lastly, there's a fallback, which is just if none of the sub-shaders succeed in compiling for your target platform, it will just fall back to a shader you've specified. You can specify diffuse, for example, which is sort of the typical thing to fall back to. We also have these program and end program keywords, which is, well, it's the scope of your actual shader code. So within those blocks, you'll only write either CG, HLSL, or GLSL. Though GLSL isn't really advised to be used by Unity, because CG can sort of cross-compile down to GLSL platforms anyway. So, yes, properties I mentioned. They're the access point, I call them, for uniforms. And they sort of do more than that. They declare, first off, they declare the base type. As you see, 2D, the textures, int is just an int, and float and range are both floating point, and color and vector are both vectors. But the difference is how they appear in the shader editor, where you have colors appear as colors, and you have ranges appear as ranges. Surprise, surprise. Yeah, so as I mentioned, there's the different base types, and they don't really decide what your type is within the shader itself, because you can sort of cast them off to the type you want to use within your shader. So for example, for vectors or colors, it sort of makes sense to talk about colors with just medium precision. You don't need all the bits, sort of, because the color is quite well defined with just a few bits anyways. So you can throw them down into the different precision floating points. So have any of you heard about float, fixed, and half before? Okay. I didn't before looking into shaders either. So have any of you seen in GLSL where you have high P and medium P and low P? Because that's the equivalent here. You have a keyword in itself which you put before your vector or your float in GLSL, where you sort of specify the same. Yes. That's interesting. Okay. Demo time, question mark. Well, there's a few things left over here to talk about. So at this point, do you understand this shader?
If not, ask. That's the opportunity right now.
Explain to me how the shader works, please.
Okay. We'll sort of get into that, but before that, there's a few things here I haven't mentioned yet, sort of. Namely the thing within there, right? There's a few sort of syntactic things I haven't talked about at all. So what's this struct? What's these pragmas? Why do I include? And so on and so forth. We'll look at that now, actually. And then I'll go back to what the shader does. Yeah, so if you think about the shaders you've been writing in GLSL, you have this thing on top where you write out the attributes, which is basically where you access all the vertex data from normally, right? That doesn't happen here. Where's the vertex data? That's a good question if you ask that, because the vertex data is kind of difficult to find within Unity. As they've described it, the data layout of the vertex buffer generally depends on a number of factors, very specific, thanks Unity, especially for meshes that are compressed and marked as non-readable. For a simple case, generally the layout is as follows. And even the general sort of description of the layout isn't specific, because you have an option to have UVs as float 2, float 3, and float 4. So yeah, it's not that simple, but we don't need to care about that too much, because we can use some predefined structures Unity have defined. So in this case, for the vertex shader, so by the way, the pragmas are just sort of declaring where the name of the shaders. So for this case, the vertex shader is the vert function. The vert function takes in app database, which is one of these predefined vertex structures. So instead of you having to write attributes, distance, this and that, you just take in the app database, and you get the position, normal, and one texture coordinate just within that structure. Are everyone following along on this? Yes or no?
No.
No. Okay. What's confusing? Everything, I imagine,
Yes.
but yes. Do you see the relation though between where you normally have the attributes listed out in GLSL, where you don't have that here?
No.
Okay. How do I explain this better? Well, actually, the next slide might help. So, in this case, I've rewritten the shader because I didn't need the UV or the texture coordinates, and I didn't need the normal or whatever was applied within the. Yeah, I didn't need neither the normal or the UV coordinates, so I wrote a new struct, vert in, and it has this weird semantic thing on the backside there, which is an HLSL specific thing, where you sort of need to declare what the purpose of a variable is, especially within these kind of structs. So in this case, you specify that, oh, I have a float 4 here, and I take that from the position data within the vertex buffer. So that's where the connection happens. So instead of having to write out the location for your attributes as you do in GLSL, you sort of just specify that, oh, I want to get the position. And then you get that. And within the HLSL and CG, you get, let's see, can I get the, yeah, there we go. You get the position, you get the normals, and you get the 4 texture coordinates, and the tangent, and the color. So this is sort of the default vertex buffer layout. You can't really change this unless you go down to a really low level. So the important thing here is just to sort of understand the connection between the semantic and getting the data from the vertex buffer that you don't really see in this shader as opposed to what you do in GLSL. Did that make it clear in any way?
A little bit.
Okay.
What's unclear?
Most of it still.
Okay, anyone else? Any other specific pointy questions? So
how would I define a normal? Could anyone guess? I already have a position there, and within my new sort of vertex input, how would I define that I also want to supply the normal with it, or do something with the normal within this shader? Yes?
You would define the float 3 with, you call it normal, for example, and then you do the same, just normally. So.
Yes, yes, very good.
Backtracking for the general understanding. So does it imply that the buffer layout is always fixed in Unity?
From my understanding, that's the case. But I think you can also delve down into the depth and sort of change this around.
But so in fact, from a beginner point of view, it's quite handy because you have a kind of a default structure that you can just align to or customize if you want. Whereas in OpenGL, you're on your own, right? In every case, right? Does it make sense?
Yes.
What's the difference between a float 2, a float 3, and a float 4?
That's a good question. I didn't think about covering those, but that's if you look at the GLSL, you have back 3, back 2, back 4, right? So it's simply vectors, but with what do you call it? Precision defined as well. So float 4 is the same as a back 4 normally in GLSL. But this too can be changed in GLSL where you have a position defined. Yes?
How do we make uniforms?
So uniforms, yes. I'll go back and let's see this slide. So uniforms are actually defined. For the shader, they're declared here, but for Unity, they're declared there. And the important thing is that you have the name matching, and then you can sort of use those externally from Unity through the editor there. But you can also access them from code by the same names. I have an example of this within the code files, I think, which are accessible on the GitLab. So for this case, for example, I have a color defined, my color, and then I declare that, oh, I also have this color in the context of the shader, and so I can tie that color up with the color here, and then use that for the output of the fragment shader.
Thank you.
So, coming back to the question about what does this shader actually do, if I go here, it simply takes the color you've defined and outputs that for all the fragments of the geometry. So I think I've supplied an example of this. Demo time, right? Demo time, actual demo time. Yeah. So I have a scene set up here with two.
We're not seeing that on screen
right.
like we're supposed to.
Good catch, thanks. Right. Oh geez, this will be tough. Let's see. So these, this is the shader I've written, and well, there's not much use in looking at this. You can see the properties that are defined. That's kind of useful. So you can see what you can access from code by looking at these. That's the same for every shader. If you look at the material here, you'll see that you'll find it under examples my shader, which is the same as the path I've specified on top here. And there's a color field which I can set my color in. Whatever. Let's see. Oh geez, this is confusing. The color field I have opened on this.
You can do mirror your own screen, right? So
that's
just
true. But but then I lose the speaker notes.
I see. Yeah. Okay. Fair enough.
Not that I really need them, but yeah. So yeah, you can set the color through here, and you can do the same through a script, which is what I've done here with the button script, which I guess we can look into. I don't think we're probably running over time just yet. So this was the way, so I appeared on the wrong screen. Right, so I have this button script. Right. And it specifies that, oh, we have a mesh renderer, which is the one holding the material in Unity. And it has a call in the update loop where you just check if the specified key is pressed. And if it's pressed, you interact with it, which means you press it or unpress it. And then from here on, you go into, oh, well, in press, we set the uniform, my color, to the pressed color. So back to the Unity inspector, we have specified that, oh, we have a pressed color, which is green, and we have unpressed color, which is the orange one. So if I run into this now, I think I specified the interact P to E as is the usual. And if I press now, it will go between those two colors. So that's how you access the uniforms and change them in code. Any questions on that? Oh, we'll go on now. So that's a simple demo. There's one thing I could probably go through here, which is this line. You might have noticed that you don't have any matrices here. And that's sort of another thing Unity's gotten rid of for you. They sort of put you on a higher level where they have the matrices hidden within this call, which is kind of bad, but in some ways it's good as well because you don't need to deal with that for just normal shaders. So previously this line was actually this. See that, I'll stand here, of course, where you have a macro for the matrix, so you can sort of inject that that value when you compile the shader, and you just multiply that by the position like you do with your normal model view projection matrix. So onto surface shaders. As I mentioned, they're a sort of higher level shader yet, so even one step up, you don't really need to deal with the lighting anymore, but instead you control the physical properties of the surface. So among these properties, you have these well, properties. Have any of you heard about these terms before? Yes? Can you explain?
I've heard about them, but I'm not sure quite how to explain them. I think we all know specularity.
Right,
I kind of
yeah.
guessed that one. Glossy is like it makes it look glossy like.
Yes.
Finance.
The
Yes.
animation is emits light.
Yes.
Yeah. Totally got metallic, so it looks more like an accurate reflects a bit more, I would imagine.
So there's a thing here actually between these properties and this. I've mentioned if you're using PBR, which is physically based rendering. We're not going to go into that really, but in PBR you sort of have these properties, the two here, the smoothness and the metallic, controlling the specularity and gloss, right?
Can I just quickly add a sort of note on the PBR thing?
Yeah.
If there's anyone who's actually interested in PBR, I think that book was just released online for free. So I can probably put that link in the GitLab page if anyone's interested.
PBR, by the way, is sort of the new modern way of rendering things, so it should be an interesting thing.
I think it was the PBR book, I'm not sure.
Read for the summer.
Yes.
What's the beat of ability to reflect light.
Can you repeat that?
The albedo property over the normal.
Right. So I think I've cheated and written them down. The albedo is, as I see it, it's the uniform color, as if it was hit by light, a white light from all angles.
Okay.
So right now we don't have a really white light from all angles, but considering the table, this probably would be some sort of shade of gray. This would be some shade of brown. That's the albedo, right? Then you have the normals, which are the same as usual. You have the emission, as was mentioned, emitting light intensities of different variants. You have the specularity and gloss. They are kind of confusing to me because they seem to be doing the same thing, but not really. In Unity, they've defined the specularity to be sort of the power of shininess from 0 to 1. So I don't really know how they defined a maximum shininess, because that seems like a property that could go on forever. And you have the gloss, which is more of the intensity of the specularity as opposed to the power of the specularity. Yes. You can actually see this a bit more clearly, I think, in another slide I have. And slideshow. That's not entirely what I wanted to do, but you can skip ahead a bit.
So, but if you use that, right, is it just a matter of plugging in that specific shader configuration and that's it?
Yes.
And you get
That's the magic of surface shaders. You just specify that, the specularity is 0.5, and then
right.
it's shiny.
So it's basically just pre-coded stuff that you guys would need to implement otherwise, right? So I mean, if you think about lighting and so on, different characteristics. But wouldn't it just be a matter of, for example, experimentation? Just try the gloss thing versus the specularity and see what's happening, right?
Yeah.
So I mean,
so I think if you have a really high power, the specular sort of point is more and more centered down. So you can see in this case, this is the smoothness, but you can see the sort of specular highlight grows more and more tiny, but more and more intense. So that's sort of both of these combined, I guess, the glossiness and the specularity. Let's jump back to the slide where we were at. Find it. We were at this one. So compared to the unleaked shader, which is basically just the one we've been, well, it's similar to the ones we've been writing in GLSL. The surface shader has the vertex stage, and it has this surface stage, and then there's another stage you're not really in control over unless you write your own lighting model that sort of just uses these properties to find the right color. Did that make sense? Somewhat. Okay, so they're cool, but you sort of lose control of the low-level stuff because you can't go into the geometry shader and the more advanced stages of the shaders using surface shaders. But they're good for doing certain things. I have an example of this as well in the source files. We'll probably jump into those as well now.
If you want to go even higher level, you can also look at the new shader graph.
That's true. Good point.
That they have, which is super cool if you want to sort of just experiment and also get a better understanding of how your data is actually transforming sort of throughout the different shaders that you create. So I would, I learned a lot from playing around in the shader graph tool.
Yeah, that's a good point. So yeah, I included a prefab from one of our, actually from our delivery in game programming, where I made a shader for this robot. The special thing about it is that it's a surface shader, but it allows you to do sort of not really normal things in the sense that you can specify a color, but you don't use that color in certain areas and stuff. So I've called it a color masked one. So you can sort of define all different colors for all different robots, which is what we did in our project. And yeah, it uses these normal, the typical textures you'll also find in surface shaders and PBR. So yeah, here you can see the relation between metallic and smoothness as well. So metallic only sort of makes it darker, but combined with smoothness, you get a really shiny sort of, you can see everything reflected in it. It's looking, giving thing, yes. Back to the presentation. The next slide. So we have a surface shader, and you might notice that the surface shader is smaller. So even though it does more, it's smaller, which kind of makes sense, seeing as you don't need to deal with the light, and you also don't really need to deal with the vertex shader. And in this case, we're doing sort of the same thing. We just apply a color, but instead of applying it directly to a fragment, we say, oh, the albedo for this fragment, because you're sort of still operating on the, you're not sort of, you're operating on the fragment level still, so all the lighting will happen in fragment, yeah, on the fragment level, instead of, yeah, vertex level. So instead of applying the color to the fragment, I applied the color to the albedo, and as you saw in the example, I think I have it here. The surface shader looks better, just because it has lighting. But that's sort of all depends on what you want to do with your shaders, right? So in a typical surface shader, you have this layout. You specify a primary surface, and then you have a surface function, just as you would with the vertex and fragment. And then you specify the lighting model, and then the viable predefined lighting models are these ones. You've been working with BPROG, hopefully. Lambert is sort of the same, but not with specular highlights, as far as I've understood. And then you have the physically based ones, which are defined by Unity, which gives you the power to, well, do more realistic looking shaders based on physical properties instead. Yeah, the comparison again, I guess. Any questions so far on surface shaders? Oh. So that's the first part. There's some resources here. This guy actually, Alan Ciccone, has a lot of cool shader stuff I really recommend looking into. This is the guy we used as resource for sort of emulating the subsurface scattering in our project for assignment 2. So I think he's written mostly for Unity, but you can use a lot of, like, if you learn how to read HLSL, you can use the same code for GLSL programs as well, without too much hassle. So I really recommend looking at the different sources. Yes.
Cool.
Let's have a break.
Cool. When do we come back? 5 past?
Good
or?
question. Yeah.
Cool. 5 past then.